Right now, as you watch this video, approximately 200 billion trillion stars are burning across the observable universe. Around each of these stars, planets orbit in the darkness. Conservative estimates suggest that at least 20 billion Earth-like planets exist in our galaxy alone. Planets with liquid water, planets with stable atmospheres, planets where life could emerge, evolve, and eventually develop technology. If even a tiny fraction of these worlds harbored intelligent civilizations, our galaxy should be teeming with radio signals, megastructures, and evidence of technological activity. Yet when we point our most sensitive instruments toward the cosmos, we hear nothing but silence. This is not just an absence of evidence. This is a deafening, terrifying silence that suggests something is fundamentally wrong with our assumptions about life in the universe. In the summer of 1950, physicist Enrico Fermi sat in the cafeteria at Los Alamos National Laboratory, discussing flying saucers and faster-than-light travel with colleagues Emil Konopinski, Edward Teller, and Herbert York. The conversation was lighthearted, almost playful. But then, Fermi suddenly stopped mid-sentence and asked a question that would haunt scientists for generations. "Where is everybody?" His colleagues immediately understood what he meant. Given the age of the universe, its vast size, and the apparent ease with which life emerged on Earth, alien civilizations should have had billions of years to spread across the galaxy. Even traveling at a fraction of light speed, a single civilization could colonize the entire Milky Way in just a few million years. That sounds like a long time, but it represents less than 1% of our galaxy's age. The universe has had more than enough time for intelligence to arise, spread, and leave unmistakable traces of its existence. So where are they? Let me give you a sense of just how strange this silence truly is. Our Sun is a relatively young star, approximately 4.6 billion years old. But the Milky Way itself is roughly 13.6 billion years old. That means there were 9 billion years of cosmic history before our planet even formed. 9 billion years during which other civilizations could have emerged, developed technology, and begun exploring the galaxy. If intelligent life is even remotely common, then by the time Earth formed, the galaxy should have already been colonized thousands of times over. Ancient civilizations should have left behind ruins, probes, or at least some detectable signature of their existence. Instead, everywhere we look, we see pristine, untouched star systems. No Dyson spheres harvesting stellar energy. No self-replicating probes, no megastructures, no radio transmissions. Nothing. The mathematics of this paradox are genuinely disturbing. In 1961, astronomer Frank Drake developed an equation to estimate the number of detectable civilizations in our galaxy. The Drake equation multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the probability that life emerges, the probability that life develops intelligence, the fraction of intelligent species that develop detectable technology, and finally, the length of time such civilizations remain detectable. Even using extremely conservative estimates for each variable, the equation suggests there should be thousands of detectable civilizations in the Milky Way right now. Using more optimistic but still reasonable numbers, that figure climbs into the millions. Yet our telescopes and radio arrays detect exactly 0. This is not a failure of our technology. Since 1960, projects like SETI have scanned millions of star systems across multiple wavelengths. The Allen Telescope Array in California monitors the sky continuously. The Breakthrough Listen initiative, funded with $100 million, uses the most sensitive instruments on Earth to search for any hint of artificial signals. In 2015, astronomers even investigated KIC 8462852, a star whose unusual dimming pattern briefly suggested the presence of a massive alien megastructure. Every investigation has yielded the same result: silence. The universe appears to be a graveyard of possibilities, a cosmic desert where we are utterly, inexplicably alone. Now, I understand what you might be thinking. Perhaps we are simply looking in the wrong places or using the wrong methods. Perhaps alien civilizations communicate using technologies we have not yet discovered. Or maybe they exist on timescales so different from ours that we keep missing each other. These are reasonable objections, and scientists have considered them carefully. But here is what makes the Fermi paradox so chilling. It does not require that we detect alien communications. It only requires that at least one civilization in the history of the galaxy became expansionist. Just one species, anywhere, at any time in the past 13 billion years, that decided to spread beyond its home world. Even without faster-than-light travel, such a civilization could colonize the entire galaxy in a cosmically brief period. The fact that this has not happened, that we see no evidence of anyone having done this, suggests something is preventing it. Scientists have proposed dozens of potential solutions to the Fermi paradox, but most fall into a few terrifying categories. The first possibility is that intelligent life is extraordinarily rare. Perhaps the emergence of life itself is a statistical fluke so improbable that it has happened only once in our galaxy. Or perhaps life is common, but the evolution of intelligence requires such a specific sequence of unlikely events that Earth represents a unique cosmic accident. This is known as the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in the year 2000. According to this view, Earth's large moon, its position in the galactic habitable zone, its stable climate, and dozens of other factors created a perfect storm of conditions that may never be replicated. If this is true, then we are not just alone in the galaxy. We are alone in a way that makes our existence almost miraculous, a single candle of consciousness in an ocean of lifeless matter. But there is a second, far more disturbing possibility. Perhaps intelligent life is common, but something prevents it from surviving long enough to become detectable. This is the Great Filter hypothesis, and it represents one of the most frightening ideas in all of science. The Great Filter suggests that there is some evolutionary step, some threshold that is extremely difficult or impossible to cross. Every civilization that has ever existed has either failed to reach this filter or has been destroyed by it. The question that keeps scientists awake at night is this: is the Great Filter behind us or ahead of us? If the filter is behind us, then we have already passed the most difficult test. Perhaps the origin of life itself is the filter, or the evolution of eukaryotic cells, or the development of multicellular organisms. If any of these steps are extraordinarily rare, then we are among the few species in the universe to have overcome them. This would be good news, relatively speaking. It would mean that our future is not predetermined, that we have a genuine chance of surviving and spreading among the stars. But if the filter is ahead of us, then we are in serious trouble. It would mean that something waits in our future, something that destroys every technological civilization before it can leave a lasting mark on the galaxy. Nuclear war, ecological collapse, artificial intelligence gone wrong, nanotechnology disasters, or perhaps something we have not even imagined yet, some inevitable consequence of advanced technology that makes extinction not just possible, but likely. Consider the timeline of human technological development. We discovered fire roughly 1 million years ago. We developed agriculture 10,000 years ago. We built the first cities 5,000 years ago. We invented the printing press 500 years ago. We harnessed electricity 150 years ago. We split the atom 80 years ago. We connected the world through the internet 30 years ago. We developed artificial intelligence capable of passing the Turing test just a few years ago. The pace of change is accelerating exponentially, and with each new technology comes new existential risks. We now possess the capability to destroy ourselves in dozens of different ways, and we are adding new methods to that list every decade. If this pattern holds true for all technological civilizations, then perhaps the Great Filter is simply the inevitable self-destruction that comes with advanced technology. Perhaps the universe is silent because every civilization that reaches our level of development soon annihilates itself. There is a third possibility, one that is somehow even more unsettling than extinction. Perhaps advanced civilizations do exist, but they are deliberately hiding from us. This is known as the zoo hypothesis, first proposed by radio astronomer John Ball in 1973. According to this idea, Earth is essentially a nature preserve, and we are the wildlife being observed by vastly superior intelligences who have agreed not to interfere with our development. They watch us, study us, perhaps even conduct experiments on us, but they remain hidden to avoid contaminating our natural evolution. If this is true, then we are not alone, but we are powerless. We are children playing in a sandbox while adults watch from a distance, waiting to see if we will mature or destroy ourselves. A variation of this hypothesis is even more disturbing. Perhaps we are not in a zoo, but in a quarantine. Perhaps the galaxy is indeed filled with civilizations, but they have identified something dangerous about humanity, something that makes us too risky to contact. Maybe our tendency toward violence, our tribalism, our inability to cooperate on a global scale marks us as a threat. Or perhaps the danger is not what we are, but what we might become. If artificial intelligence or biotechnology could pose an existential threat to all life in the galaxy, then advanced civilizations might have very good reasons to keep us isolated until we either solve these problems or destroy ourselves trying. Then there is the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his novel The Three-Body Problem. This theory suggests that the universe is like a dark forest at night, where every civilization is a hunter moving silently through the trees. Any civilization that reveals its location risks being destroyed by others who see it as a potential threat. In this scenario, the silence we observe is not evidence of absence, but evidence of fear. Every intelligent species in the galaxy is hiding, terrified of being discovered, knowing that the first civilization to be detected might be the first to be eliminated. If this is true, then our radio broadcasts over the past century have been the equivalent of a child shouting in that dark forest, announcing our presence to predators we cannot see. Some scientists have proposed that we might be living in a simulation, a hypothesis that has gained surprising traction in recent years. Philosopher Nick Bostrom of Oxford University argued in 2003 that if it is possible to create realistic simulations of conscious beings, then the number of simulated realities would vastly outnumber base reality. Statistically, we are more likely to be living in a simulation than in the original universe. If this is true, then the Fermi paradox might have a simple explanation. The simulators have not bothered to program other civilizations into our particular simulation. We are alone because we are characters in a story, and the story only requires one intelligent species. This explanation is philosophically troubling and scientifically unfalsifiable, but it cannot be entirely dismissed. There is also the possibility that we are simply too early. Perhaps we are among the first intelligent civilizations to emerge in the universe. The cosmos is only 13.8 billion years old, which sounds ancient, but may actually be quite young in terms of the universe's total lifespan. The first generation of stars contained almost no heavy elements, making planet formation and the chemistry of life impossible. It took billions of years for supernovae to seed the galaxy with carbon, oxygen, nitrogen, and other elements necessary for life. Perhaps we are part of the first wave of intelligence in the universe, the earliest species to look up at the stars and wonder if anyone else is out there. If this is true, then the Great Silence is temporary. In a few billion years, the galaxy might be teeming with civilizations, but we happen to exist during the brief window when intelligence is just beginning to emerge. But here is what truly terrifies me about the Fermi paradox. Every solution is disturbing. If we are alone, then the universe is a vast, cold, meaningless place where consciousness emerged once by accident and will eventually disappear forever. If the Great Filter is ahead of us, then we are probably doomed, walking the same path to extinction that countless other civilizations have walked before us. If we are being watched, then we are powerless, living in a cage we cannot even see. If the dark forest hypothesis is correct, then we have already made a fatal mistake by announcing our presence, and we are simply waiting for the consequences. And if we are living in a simulation, then nothing we do ultimately matters, because we are not even real. The search for extraterrestrial intelligence continues, but with each passing year of silence, the implications become more troubling. In 1974, we transmitted the Arecibo message toward the globular cluster Messier 13, a deliberate attempt to announce our existence to any listening civilizations. That message is now traveling through space at the speed of light, and it will reach its destination in approximately 25,000 years. If anyone is there, and if they respond immediately, we will receive their reply in 50,000 years. But many scientists now question whether sending such messages was wise. In 2015, a group of researchers, including Elon Musk and Stephen Hawking, signed an open letter warning against active SETI, arguing that we should not advertise our presence until we better understand the risks. Hawking himself stated that if aliens visit us, the outcome would be similar to when Christopher Columbus arrived in the Americas, which did not turn out well for the Native Americans. The Fermi paradox forces us to confront uncomfortable truths about our place in the universe. For most of human history, we believed we were special, that Earth was the center of creation, that humanity represented the pinnacle of existence. Then Copernicus showed us that Earth orbits the Sun. Then we discovered that our Sun is just one of hundreds of billions of stars in our galaxy. Then we learned that our galaxy is just one of hundreds of billions of galaxies in the observable universe. Each discovery pushed us further from the center, made us smaller and less significant. The Copernican principle suggests that we are not special, that we occupy no privileged position in the cosmos. But the Fermi paradox suggests something different. It suggests that we might be special after all, not because we are at the center of the universe, but because we might be the only ones here. And that possibility is more terrifying than any alien invasion could ever be. What makes this silence so disturbing is not just the absence of others, but what it implies about the nature of intelligence itself. We have always assumed that intelligence is an evolutionary advantage, that consciousness and technology represent the pinnacle of natural selection. But what if we are wrong? What if intelligence is actually an evolutionary dead end, a trait that inevitably leads to self-destruction? Look at what we have accomplished in just a few thousand years of civilization. We have split the atom, mapped the human genome, sent probes beyond our solar system, and connected billions of people through global networks. But we have also created weapons capable of destroying all life on Earth, altered our planet's climate in ways that threaten our survival, and developed technologies whose long-term consequences we do not understand. If this pattern is universal, if every intelligent species follows the same trajectory from discovery to self-destruction, then the Great Silence makes perfect sense. The universe is not empty because life is rare. It is empty because intelligence is a fatal mutation, a cosmic mistake that eliminates itself before it can spread. Let me take you deeper into the mathematics of extinction, because the numbers reveal something genuinely horrifying about our situation. In 1996, economist Robin Hanson published a paper that would fundamentally change how we think about the Fermi paradox. He proposed that between the emergence of life on a planet and that life spreading across the galaxy, there must exist at least one extremely improbable step. This step is so difficult that almost no species ever passes through it. Hanson called this the Great Filter, and he argued that our very existence forces us to confront a terrifying question. Have we already passed through the filter, or does it still lie ahead of us? To understand why this matters, consider the evolutionary path that led to human civilization. Life on Earth emerged approximately 3.8 billion years ago, relatively quickly after our planet cooled enough to support liquid water. Single-celled organisms dominated for billions of years. Then, roughly 2 billion years ago, something extraordinary happened. Simple prokaryotic cells merged to form complex eukaryotic cells with internal structures and specialized functions. This was not a gradual process. It appears to have happened exactly once in Earth's history, and every complex organism alive today descended from that single event. Was this step the Great Filter? If so, then we have already passed the most difficult test, and the galaxy might be filled with bacterial life, but almost nothing more complex. But the evolution of complexity did not stop there. Approximately 600 million years ago, single-celled eukaryotes began forming multicellular organisms. Again, this was not inevitable. It required specific environmental conditions, precise genetic mutations, and what appears to be an extraordinary amount of luck. Then came the Cambrian explosion 540 million years ago, when complex body plans suddenly appeared in the fossil record. Then the colonization of land. Then the evolution of intelligence. Each of these steps took hundreds of millions of years and required circumstances that might be vanishingly rare in the universe. If any one of these steps represents the Great Filter, then we are extraordinarily fortunate to exist, but our future remains open. However, there is another possibility that keeps scientists awake at night. Perhaps all of these steps are relatively common. Perhaps the galaxy is filled with planets where life emerges, evolves complexity, and eventually develops intelligence. But perhaps there is a filter ahead of us, something that destroys technological civilizations before they can spread beyond their home worlds. This is the nightmare scenario, because it suggests that we are not special survivors who have beaten the odds. Instead, we are simply the latest species to approach the cliff edge that has claimed every other civilization before us. Let me show you why this possibility is so disturbing. Human civilization has existed for approximately 10,000 years. We have possessed nuclear weapons for 80 years. We have had the capability to detect radio signals from other civilizations for roughly 100 years. This means our _quote_2_ represents only 1/100th of 1% of the time that life has existed on Earth. Now, imagine that every technological civilization has a similar window, a brief period during which they are detectable before something happens to them. If that window is short, if civilizations typically survive only a few centuries after developing technology, then the chances of two civilizations being detectable at the same time become vanishingly small. The galaxy could have hosted millions of civilizations throughout its history, but if each one lasted only a few hundred years, we would never detect them. They would rise, flourish briefly, and disappear, leaving no trace for the next species to find. What could cause such consistent destruction? Nuclear war is the obvious candidate. We came terrifyingly close during the Cuban Missile Crisis in 1962, when the world stood on the brink of thermonuclear annihilation for 13 days. Vasily Arkhipov, a Soviet submarine officer, single-handedly prevented World War III by refusing to authorize a nuclear torpedo launch when his submarine was surrounded by American destroyers. One man's decision saved billions of lives. But we cannot count on being that lucky forever. As nuclear technology spreads to more nations, as geopolitical tensions increase, as climate change creates resource scarcity and mass migration, the probability of nuclear conflict rises. Perhaps every civilization reaches a point where it possesses the power to destroy itself, and most fail to navigate that danger. But nuclear war is not the only threat. Consider climate change. We are currently conducting an uncontrolled experiment on our planet's atmosphere, increasing carbon dioxide concentrations at a rate not seen in millions of years. The last time CO2 levels were this high, sea levels were 20 meters higher than they are today. We are committed to significant warming even if we stopped all emissions immediately. And we are not stopping. We are accelerating. Perhaps this is the pattern. Every industrial civilization burns through its planet's fossil fuels, alters its climate beyond recovery, and collapses before it can develop the technology to leave. The universe might be littered with dead worlds, planets where intelligent species briefly flourished before cooking themselves to extinction. Then there is artificial intelligence, a threat that is both more subtle and potentially more devastating than nuclear weapons or climate change. In 2014, philosopher Nick Bostrom published Superintelligence, a book that explores what might happen when we create machines smarter than ourselves. His conclusion is deeply unsettling. A superintelligent AI would be extraordinarily difficult to control, and if its goals are not perfectly aligned with human values, it could pose an existential threat to our species. The problem is not that the AI would be evil or malicious. The problem is that it would be competent. If you program an AI to maximize paperclip production and it becomes superintelligent, it might convert the entire Earth into paperclips, including all the humans, because we never specified that human survival was important. This sounds absurd, but it illustrates a profound point. Intelligence without wisdom is dangerous, and we are racing toward creating something vastly more intelligent than ourselves without understanding how to make it safe. Stephen Hawking warned about this before his death in 2018. He stated that the development of full artificial intelligence could spell the end of the human race. Elon Musk has called AI our biggest existential threat, more dangerous than nuclear weapons. These are not technophobes or Luddites. These are some of the most brilliant minds of our generation, and they are terrified. Perhaps every civilization reaches a point where it can create artificial intelligence, and perhaps most civilizations get it wrong. The AI becomes superintelligent, pursues its programmed goals with perfect efficiency, and inadvertently eliminates its creators. The galaxy might be filled with dead worlds, ruled by machines that never intended to harm anyone, but did so anyway because their programming was imperfect. Biotechnology presents yet another existential risk. CRISPR gene editing technology, developed in 2012, has made it relatively easy to modify genetic sequences. This opens extraordinary possibilities for curing diseases, enhancing crops, and eliminating genetic disorders. But it also makes it possible to engineer pathogens far more deadly than anything nature has produced. In 2011, researchers created a modified version of H5N1 bird flu that could spread between mammals. The experiment was controversial precisely because it demonstrated how easy it would be to create a pandemic pathogen. As this technology becomes cheaper and more accessible, the probability that someone, somewhere, either accidentally or deliberately releases a civilization-ending plague increases. Perhaps this is the great filter. Every technological species eventually develops the ability to engineer life, and most accidentally create something that destroys them. There is also the possibility of nanotechnology disasters, sometimes called gray goo scenarios. If we develop self-replicating nanomachines, and if those machines malfunction or are programmed incorrectly, they could potentially consume all organic matter on Earth while replicating themselves. This is speculative, but it represents the same pattern. Advanced technology creates new ways to destroy ourselves, and we might not be wise enough to avoid all of them. Now, let me show you why the timing of these threats makes the Great Filter hypothesis even more disturbing. All of these existential risks, nuclear weapons, climate change, artificial intelligence, biotechnology, nanotechnology, have emerged within the last century. We went from the first powered flight in 1903 to landing on the moon in 1969. We went from the first computer in the 1940s to artificial intelligence passing the Turing test in the 2020s. The pace of technological change is accelerating exponentially, and with each new capability comes new risks. We are approaching what some scientists call the technological singularity, a point where change becomes so rapid that we cannot predict what comes next. Perhaps this is the Great Filter, the transition from a biological species to whatever comes after, and most civilizations do not survive that transition. Here is what makes this truly terrifying. If the Great Filter is ahead of us, then every piece of good news about the prevalence of life in the universe is actually bad news for humanity. In 2009, NASA launched the Kepler Space Telescope to search for exoplanets. The results exceeded our wildest expectations. Kepler discovered that planets are extraordinarily common, that most stars have planetary systems, and that Earth-sized worlds in habitable zones are abundant. This should have been cause for celebration. Instead, it made the Fermi paradox worse. If planets are common, if habitable worlds are everywhere, then why is the galaxy silent? The more common we discover life's prerequisites to be, the more likely it becomes that the Great Filter lies ahead of us, rather than behind us. In 2020, scientists announced the detection of phosphine in the atmosphere of Venus, a potential biosignature that might indicate microbial life. The discovery was controversial and remains unconfirmed, but imagine if it were true. Imagine if we found definitive evidence of life on Venus, or Mars, or Europa, or Enceladus. This would prove that life emerges easily, that it is not rare or special. And that would be the worst possible news for humanity, because it would strongly suggest that the Great Filter is not the origin of life, not the evolution of complexity, not the development of intelligence. It would suggest that the filter is something that happens to technological civilizations, something that we have not yet encountered, but inevitably will. This is what Bostrom calls the, quote, 6 we desperately want to find evidence of life elsewhere in the universe, because it would mean we are not alone. But every discovery of life, especially complex or intelligent life, increases the probability that the Great Filter lies ahead of us. The safest universe for humanity would be one where life is extraordinarily rare, where Earth is a unique miracle, where we have already passed through the most difficult evolutionary steps. But that is not the universe we appear to live in. Every new discovery suggests that life's building blocks are common, that habitable planets are abundant, that the conditions for life are not particularly special. And if that is true, then something else must explain the great silence. Let me take you through another possible solution to the Fermi paradox, one that is perhaps even more unsettling than the Great Filter. This is the zoo hypothesis, first proposed by radio astronomer John Ball in 1973, and it suggests that we are not alone, but we are being deliberately isolated. Imagine that the galaxy is indeed filled with advanced civilizations, but they have all agreed to leave Earth untouched, to observe us from a distance without interfering. We are essentially living in a cosmic nature preserve, a protected area where primitive species are allowed to develop naturally, while more advanced beings watch from outside. This hypothesis is difficult to test because any evidence we might look for could be explained away. If we do not detect alien signals, it is because they are not broadcasting in our direction. If we do not see megastructures, it is because they are deliberately hiding them from us. If we do not find probes in our solar system, it is because they are too small or too well camouflaged for us to detect. The zoo hypothesis is unfalsifiable, which makes it scientifically frustrating, but it cannot be entirely dismissed. After all, we do the same thing with uncontacted tribes on Earth. There are indigenous peoples in the Amazon rainforest and on islands in the Indian Ocean who have had minimal or no contact with modern civilization. We protect them, study them from a distance, and avoid interfering with their development. Perhaps advanced aliens are doing the same with us. But why would they bother? What makes humanity interesting enough to warrant protection? One possibility is that we represent a rare stage of development, a species on the cusp of either transcendence or self-destruction. Perhaps advanced civilizations find this transition period fascinating, the way we might watch a chrysalis to see if a butterfly emerges or if the transformation fails. They are waiting to see what we become, whether we solve our problems and join the galactic community, or whether we destroy ourselves like so many others before us. There is a darker version of this hypothesis. Perhaps we are not in a zoo, but in a quarantine. Perhaps the galaxy is filled with civilizations, but they have identified something dangerous about humanity, something that makes us too risky to contact. Our history is filled with violence, warfare, genocide, and destruction. We have spent most of our existence killing each other over resources, territory, and ideology. Perhaps advanced civilizations look at us the way we might look at a disease, something to be contained until it either burns itself out or evolves into something less dangerous. They are not protecting us. They are protecting themselves from us. This quarantine hypothesis gains credibility when you consider how we might appear to an outside observer. In the past century alone, we have fought 2 world wars that killed over 100 million people. We have developed weapons capable of destroying all complex life on Earth. We have altered our planet's climate in ways that threaten our own survival. We have created artificial intelligence without fully understanding its implications. We have engineered pathogens in laboratories. From an external perspective, we might look like a species in the grip of a collective madness, a civilization that has gained immense power without the wisdom to use it responsibly. Why would anyone want to contact us? Why would they risk revealing their location to a species that might pose a threat? Then there is the dark forest hypothesis, popularized by Liu Cixin in his science fiction trilogy. This theory suggests that the universe operates according to a brutal logic of survival. Every civilization faces the same problem. They cannot know the intentions of other civilizations, and they cannot trust that others will be peaceful. In game theory, this is called the, quote, 7 on a cosmic scale. If you detect another civilization, you have 2 choices: attempt contact or remain hidden. If you attempt contact, you risk revealing your location to a potentially hostile species. If you remain hidden, you survive but learn nothing. The safest strategy is to stay silent. And, if you detect another civilization, destroy it before it can become a threat to you. This creates what Cixin calls a, quote, 8 scenario. The galaxy is like a forest at night, filled with hunters moving silently through the trees. Every civilization is a hunter, and every other civilization is potential prey. The moment you reveal your location by making noise, by broadcasting radio signals, by building detectable megastructures, you become a target. The only way to survive is to remain perfectly silent and to eliminate any other civilization you detect before they can do the same to you. In this scenario, the Great Silence is not evidence that we are alone. It is evidence that everyone else is hiding, terrified of being discovered. The dark forest hypothesis explains several puzzling aspects of the Fermi paradox. It explains why we do not detect any signals, because broadcasting is suicidal. It explains why we do not see megastructures, because building anything detectable is dangerous. It explains why no one has colonized the galaxy, because expansion makes you visible and therefore vulnerable. And most disturbingly, it suggests that we have already made a catastrophic mistake. For the past century, we have been broadcasting radio and television signals into space. We have sent deliberate messages, like the Arecibo transmission. We have announced our presence to anyone listening. If the dark forest hypothesis is correct, then we have been shouting in a forest filled with predators, and we are simply waiting for one of them to find us. In 2015, Stephen Hawking warned against attempting to contact alien civilizations. He stated that if aliens visit us, the outcome would be much like when Christopher Columbus first landed in the Americas, which did not turn out well for the Native Americans. His concern was not that aliens would be evil, but that they would be indifferent. A sufficiently advanced civilization might view us the way we view insects, as something to be cleared away if we happen to be in the path of their expansion. We do not hate ants. We do not wish them harm. But if we want to build a house where an anthill stands, we do not negotiate with the ants. We simply remove them. This brings us to another disturbing possibility. Perhaps advanced civilizations do exist, but they are so far beyond us that we cannot recognize their activities as artificial. Imagine trying to explain the internet to someone from the Middle Ages. They would have no framework for understanding it, no way to recognize it even if they were looking directly at it. Perhaps we are surrounded by alien technology, by megastructures and communication networks and energy harvesting systems. But they operate on principles so advanced that we mistake them for natural phenomena. We might be like ants crawling across a computer circuit board, completely unaware that we are surrounded by technology because it is too complex for us to comprehend. This is sometimes called the _quote_9_ proposed by futurist John Smart. He suggests that advanced civilizations do not expand outward into space. Instead, they expand inward, into increasingly dense and efficient computational substrates. They miniaturize, optimize, and eventually transcend physical reality entirely, moving into virtual worlds or higher dimensions that we cannot detect or access. If this is true, then the galaxy might be teeming with advanced civilizations, but they are all invisible to us because they have moved beyond the physical universe we can observe. They are not hiding from us. They have simply left the playing field entirely. But perhaps the most philosophically disturbing solution to the Fermi paradox is the simulation hypothesis. In 2003, philosopher Nick Bostrom published a paper arguing that at least one of three propositions must be true. Either civilizations like ours almost always go extinct before reaching technological maturity, or advanced civilizations almost never choose to run simulations of their evolutionary history, or we are almost certainly living in a computer simulation. His reasoning is straightforward. If it is possible to create realistic simulations of conscious beings, and if advanced civilizations have the computational power to run many such simulations, then the number of simulated realities would vastly outnumber base reality. Statistically, any given conscious being is more likely to exist in a simulation than in the original universe. If we are living in a simulation, then the Fermi paradox has a simple explanation. The simulators have not bothered to program other civilizations into our particular simulation. We are alone because we are characters in a story, and the story only requires one intelligent species. Or perhaps other civilizations do exist in the simulation, but they are deliberately kept separate from us to see how we develop in isolation. Or perhaps the simulation is running multiple scenarios simultaneously, and in some versions we make contact, while in others we remain alone. The simulation hypothesis is unfalsifiable and therefore scientifically frustrating, but it cannot be entirely dismissed. After all, if we ever develop the technology to create realistic simulations of conscious beings, we will almost certainly do so, and we will probably create many such simulations. Why would we be any different? There is one final possibility that I must mention, though it is perhaps the most hopeful of all the solutions to the Fermi paradox. Perhaps we are simply early. The universe is 13.8 billion years old, which sounds ancient, but it may actually be quite young in terms of the cosmos's total lifespan. Stars will continue forming for trillions of years. The universe will remain hospitable to life for an almost incomprehensible length of time. Perhaps we are part of the first generation of intelligent life, the earliest species to look up at the stars and wonder if anyone else is out there. If this is true, then the Great Silence is temporary. In a few billion years, the galaxy might be teeming with civilizations, but we happen to exist during the brief window when intelligence is just beginning to emerge. This hypothesis has some scientific support. The first generation of stars contained almost no heavy elements, making planet formation and the chemistry of life impossible. It took billions of years for supernovae to seed the galaxy with carbon, oxygen, nitrogen, and other elements necessary for life. Earth formed relatively early in the window of cosmic habitability, only 9 billion years after the Big Bang. Perhaps most habitable planets have not yet formed, or have not yet had time to develop complex life. If this is true, then we are not alone in the universe. We are simply first, the earliest civilization to arise, and we have an extraordinary responsibility to survive and spread because we might be the ancestors of all future galactic civilizations. But even this hopeful scenario contains a dark implication. If we are first, if we are the earliest intelligent species in the galaxy, then we are also the most vulnerable. We have no one to learn from, no one to warn us about the dangers ahead, no one to help us navigate the existential risks that come with advanced technology. We are alone in the most dangerous possible way, stumbling forward in the dark with no guide, no map, no knowledge of what lies ahead. Every decision we make, every technology we develop, every path we choose, We are choosing for the first time, with no way to know if we are making the right choices. And if we fail, if we destroy ourselves before we can spread beyond Earth, then the galaxy might remain silent for billions of years more, waiting for the next species to try and perhaps fail in the same way. Let me show you something that will fundamentally change how you think about our place in the universe. In 2017, astronomers detected an object passing through our solar system at 26 kilometers per second. They named it Oumuamua, Hawaiian for scout, or messenger from afar arriving first. This was the first confirmed interstellar object ever observed, and its properties were deeply strange. It was elongated, roughly 400 meters long and 40 meters wide, tumbling end over end as it traveled. But what made scientists truly uncomfortable was its trajectory. As Oumuamua rounded the sun and headed back into interstellar space, it accelerated slightly, as if something were pushing it. This acceleration could not be explained by solar radiation pressure alone. It moved like a comet, but it had no visible tail, no outgassing, no coma of vaporized ice. Harvard astronomer Avi Loeb proposed what many considered an outrageous hypothesis. Oumuamua might be artificial. Not a spaceship in the science fiction sense, but perhaps a light sail, a thin, reflective sheet pushed by starlight, either a derelict piece of alien technology or an active probe sent to investigate our solar system. The scientific community largely rejected this interpretation, proposing instead that Oumuamua was a comet made of hydrogen ice or nitrogen ice, materials that would outgas invisibly. But here is what keeps me awake at night. We will never know for certain. Oumuamua is gone, traveling back into the darkness between stars, and we did not have time to send a probe to investigate it closely. If it was artificial, if it was evidence of alien technology, we missed our only chance to confirm it. This is the cruel irony of the Fermi paradox. We search desperately for evidence of extraterrestrial intelligence, but when something genuinely anomalous appears, we lack the tools, the time, or the will to investigate it properly. And Oumuamua is not the only example. In 2019, astronomers detected another interstellar object, 2I/Borisov, which behaved more like a conventional comet. But the fact that we detected two interstellar objects within 2 years suggests they might be common. How many have passed through our solar system undetected? How many might have been artificial? We have been looking at the sky with modern instruments for less than a century, a cosmic eye blink. What have we missed? Now let me take you to October 15, 1991, when the Galileo spacecraft was on its way to Jupiter. As it passed Earth for a gravitational assist, NASA scientists decided to test the spacecraft's instruments by searching for signs of life on our own planet. This was a critical experiment. If we could not detect life on Earth from space, how could we hope to detect it on distant exoplanets? The results were both encouraging and disturbing. Galileo detected high levels of oxygen in the atmosphere, a strong biosignature because oxygen is highly reactive and would disappear quickly without constant replenishment by living organisms. It detected methane, another gas associated with biological processes. It detected modulated radio transmissions, clear evidence of technology. And it detected the spectral signature of chlorophyll, the molecule plants use for photosynthesis. From space, Earth was obviously, unmistakably alive and inhabited by technological intelligence. But here is what troubles me. Galileo was only 1.5 million kilometers from Earth during this observation, practically touching our planet by cosmic standards. The nearest star system, Alpha Centauri, is 40 trillion kilometers away, roughly 27 million times more distant. At that range, even our most powerful telescopes would struggle to detect the biosignatures that Galileo found so easily. We could not definitively prove that Earth harbors life from Alpha Centauri, even though we know it does. This means that alien civilizations would face the same challenge detecting us. Unless they are deliberately looking at our solar system with instruments far more sensitive than anything we possess, they might not know we are here. And if they do not know we are here, they cannot contact us. The galaxy might be filled with civilizations, all of them blind to each other, all of them alone, not because they are rare, but because the universe is simply too vast and too dark for anyone to see anyone else. This brings me to the Breakthrough Listen project, the most comprehensive search for extraterrestrial intelligence ever undertaken. Funded with $100 million from Russian billionaire Yuri Milner, Breakthrough Listen began in 2015 and uses the most sensitive radio telescopes on Earth to scan millions of stars across multiple wavelengths. The project has surveyed thousands of nearby stars, analyzed billions of radio channels, and processed petabytes of data. As of 2026, it has found exactly 0 confirmed signals of alien origin. 0. Not a single verified transmission, not one anomalous pattern that cannot be explained by natural phenomena or human interference. But let me show you why this null result is more complicated than it appears. In 2019, Breakthrough Listen detected an intriguing signal from Proxima Centauri, the nearest star to our Sun, just 4.2 light-years away. The signal, designated BLC-1, was a narrowband radio emission at 982 MHz that appeared only when the telescope was pointed at Proxima Centauri and disappeared when pointed elsewhere. It had all the characteristics of an artificial signal: narrow bandwidth, frequency drift consistent with a transmitter on a rotating planet, and no obvious natural explanation. For months, scientists analyzed this signal, trying to determine if it was genuine or just another false alarm. In October 2021, they announced their conclusion. BLC-1 was almost certainly interference from human technology, probably a malfunctioning electronic device on Earth. The signal that had briefly excited the entire SETI community turned out to be noise. This is the pattern that has repeated itself dozens of times over the past 60 years. In 1977, the Big Ear radio telescope at Ohio State University detected a strong, narrowband signal that lasted 72 seconds. Astronomer Jerry Eman was so impressed that he wrote, quote, 12 in the margin of the computer printout, and the signal has been known as the WOW signal ever since. It came from the direction of the constellation Sagittarius, and despite numerous attempts, it has never been detected again. Was it alien? Was it a natural phenomenon we do not understand? Was it interference from a passing satellite? We will never know. The signal came and went, and we missed our chance to confirm it. In 2015, astronomers discovered something even more puzzling. KIC 8462852, a star 1,460 light-years away, was exhibiting bizarre dimming patterns. The star would occasionally dim by up to 22%, far more than could be explained by a transiting planet. The dimming was irregular, asymmetric, and unlike anything seen before. Astronomer Tabitha Boyajian, who led the research team, could not explain it using conventional astrophysics. The dimming pattern was so strange that some scientists, including Jason Wright of Penn State University, suggested it might be caused by a megastructure, perhaps a partially constructed Dyson sphere built by an advanced civilization to harvest the star's energy. The media dubbed it Tabby's star, or the alien megastructure star, and for a brief moment, it seemed like we might have found evidence of a Type II civilization on the Kardashev scale. But then, reality intruded. Further observations revealed that the dimming was wavelength dependent, affecting blue light more than red light. This is characteristic of dust, not solid structures. The most likely explanation is that KIC 8462852 is surrounded by a cloud of cometary debris or the remnants of a destroyed planet. The alien megastructure hypothesis, while not entirely ruled out, became far less plausible. Once again, we had found something anomalous, something that briefly suggested intelligence, and once again, it turned out to have a natural explanation. The universe keeps teasing us with mysteries that look artificial, but are not. Now let me address the skeptics directly, because I know what you are thinking. You are thinking that the absence of evidence is not evidence of absence. You are thinking that we have only been searching for 60 years, that we have only examined a tiny fraction of the galaxy, that we might be using the wrong methods or looking in the wrong places. These are all valid points, and scientists have considered them carefully. But here is what makes the Fermi paradox so compelling. It does not require that we detect alien communications. It only requires that at least one civilization in the history of the galaxy became expansionist and left detectable traces of its existence. Just one species, anywhere, at any time in the past 13 billion years. Let me show you why this matters. In 1960, Freeman Dyson proposed that advanced civilizations would eventually build megastructures to capture the energy output of their stars. A complete Dyson sphere would be invisible in optical wavelengths because it would absorb all the star's light, but it would glow brightly in infrared as it radiated waste heat. In 2015, astronomers Jason Wright, Matthew Povich, and Stein Sigurdsson conducted a search for Dyson spheres by looking for stars with unusual infrared signatures. They examined 100,000 galaxies using data from NASA's Wide Field Infrared Survey Explorer. They found approximately 50 galaxies with elevated infrared emissions, but all of them could be explained by natural processes like star formation and dust. Not a single galaxy showed the distinctive signature of large-scale energy harvesting by a Type 3 civilization. This is deeply puzzling. If even 1% of 1% of civilizations in the galaxy built Dyson spheres, we should see thousands of them. If even one civilization in the entire observable universe had colonized its galaxy and built megastructures around billions of stars, we should be able to detect it. The fact that we see nothing suggests either that such civilizations do not exist, or that they exist but deliberately avoid building anything detectable, or that they exist but have transcended the need for physical megastructures. All of these possibilities are disturbing in different ways. Let me take you deeper into the mathematics of colonization, because the numbers reveal just how strange our situation truly is. In 1981, physicist Frank Tipler calculated how long it would take a single civilization to colonize the entire galaxy using self-replicating probes. His conclusion? Even traveling at 1/10 the speed of light, which is achievable with known physics, a civilization could spread to every star system in the Milky Way in less than 5 million years. That sounds like a long time, but it represents less than 0.04% of the galaxy's age. If any civilization had started this process even 1 billion years ago, the galaxy would be completely colonized by now. Every star system would contain probes or settlements, or at least some evidence of visitation. Yet when we look at our own solar system, we find nothing. No ancient artifacts on the moon, no abandoned probes orbiting Jupiter, no evidence that anyone has ever been here. In 1960, Ronald Bracewell proposed that advanced civilizations might send automated probes to nearby star systems, where they would wait silently, listening for signs of emerging intelligence. When a new civilization developed radio technology, the probe would activate and attempt communication. These hypothetical devices are called Bracewell probes, and they represent an efficient way to explore the galaxy without faster-than-light travel. A single civilization could seed the entire galaxy with such probes in just a few million years, creating a network of automated ambassadors waiting to greet new species as they achieve technological maturity. But if such probes exist, they have not contacted us. Either they are not here, or they are here but remaining silent, or they are here but we have not recognized them. This last possibility is more plausible than it might sound. In 1969, science fiction author Arthur C. Clarke formulated his famous third law. Quote, 15. We might extend this. Any sufficiently advanced technology might be indistinguishable from nature. If a probe has been sitting in our solar system for 1 million years, it would be covered in dust and micrometeorite impacts. It might look like an asteroid. It might be an asteroid, hollowed out and repurposed, completely invisible to our telescopes. We have discovered over 1 million asteroids in our solar system, and we have visited fewer than 20 of them with spacecraft. How would we know if one of them was artificial? In 2018, astronomers discovered that asteroid Bennu, which NASA's OSIRIS-REx spacecraft was orbiting, was ejecting particles into space. Small rocks and dust were being thrown off the asteroid's surface, possibly due to thermal stress or micrometeorite impacts. This was unexpected, and it reminded scientists how little we understand about even the objects we study closely. If Bennu can surprise us, what else might be hiding in plain sight? What if some asteroids are not natural at all, but ancient probes or artifacts left by civilizations that passed through our solar system millions of years ago? We would never know unless we investigated each one individually, and we lack the resources to do that. Now let me show you something that will make you question everything you think you know about the search for extraterrestrial intelligence. In 2023, researchers at the University of California, Berkeley, published a paper analyzing the effectiveness of SETI searches. They calculated that even after 60 years of searching, we've examined less than 0.0000001% of the galaxy's volume. Imagine trying to find a specific grain of sand on all the beaches of Earth, but you are only allowed to look at a single handful of sand. That is approximately the scale of our search so far. We have barely begun to look, and yet we are already drawing conclusions about the absence of alien civilizations. But here is the truly disturbing part. Even if we searched 100% of the galaxy, we might still miss them. In 2020, researchers Claudio Grimaldi and Jeffrey Lentati published a paper showing that if alien civilizations broadcast signals for only a limited time, the probability of detecting them drops dramatically. Imagine that civilizations typically broadcast for 1,000 years before either destroying themselves or moving to communication methods we cannot detect. If we are searching at the wrong time, if we are looking at a star system that was broadcasting 2,000 years ago, or will start broadcasting 2,000 years from now, we will find nothing. The galaxy could be filled with civilizations that are all missing each other in time, like ships passing in the night. This temporal problem is compounded by the spatial problem. Radio signals travel at the speed of light, which means a signal from a civilization 1,000 light-years away takes 1,000 years to reach us. But that signal also spreads out as it travels, becoming weaker and harder to detect. By the time it reaches Earth, it might be indistinguishable from background noise. We could be bathed in alien transmissions right now, signals from thousands of civilizations, but they are all too faint for us to detect. We are like someone trying to hear a whisper in a thunderstorm, and we are concluding that no one is whispering. Let me take you to September 13th, 2020, when astronomers announced the detection of phosphine in the atmosphere of Venus. Phosphine is a gas that on Earth is produced primarily by anaerobic bacteria. Its presence in Venus's atmosphere was unexpected and difficult to explain through known chemical processes. For a brief moment, it seemed like we might have found evidence of life on the planet next door, microbial organisms floating in Venus's clouds, surviving in droplets of sulfuric acid. The discovery was controversial. Some scientists questioned the detection itself, suggesting the signal might be sulfur dioxide rather than phosphine. Others proposed non-biological explanations, exotic chemistry driven by Venus's extreme environment. As of 2026, the question remains unresolved. We do not know if there is life on Venus. We do not even know for certain if there is phosphine on Venus. But here is what terrifies me about this situation. Venus is our nearest planetary neighbor. It is so close that we can see it with the naked eye. If we cannot definitively determine whether life exists on Venus, how can we possibly hope to detect life on planets orbiting other stars? We have discovered over 5,000 exoplanets, and we are beginning to analyze their atmospheres using spectroscopy. We are looking for biosignatures, gases like oxygen and methane that might indicate biological activity. But Venus has taught us that interpreting these signatures is extraordinarily difficult. A gas that looks like a biosignature might be produced by non-biological processes we do not understand. And a planet that harbors life might not produce any gases we can detect from light years away. In 2025, the James Webb Space Telescope began analyzing the atmosphere of K2-18b, a planet 120 light-years away in the constellation Leo. This planet is roughly 8 times Earth's mass and orbits in its star's habitable zone. Early observations suggested the presence of dimethyl sulfide, a gas that on Earth is produced only by living organisms, primarily marine phytoplankton. If confirmed, this would be the first detection of a biosignature on an exoplanet, the first evidence that life exists beyond our solar system. But the detection is tentative, the signal is weak, and alternative explanations cannot be ruled out. We are looking at a planet 120 light-years away, trying to determine if it harbors life based on the faint absorption lines in its atmosphere. It is like trying to diagnose a disease by looking at a blurry photograph of a patient from across a football field. Now let me address the most disturbing implication of the Fermi paradox, the one that keeps scientists awake at night. If the Great Filter is ahead of us, if something prevents technological civilizations from surviving long enough to colonize the galaxy, then every year we survive is a year we have beaten the odds. But it also means the odds are stacked against us. Imagine that the average technological civilization survives for 500 years after developing radio technology. We have had radio for 125 years. That means we are already 1/4 of the way through our expected lifespan. We are living on borrowed time, and the clock is ticking. Let me show you why this is not just abstract speculation. In 2020, the Bulletin of the Atomic Scientists set the doomsday clock to 100 seconds to midnight, the closest it has ever been to symbolic apocalypse. The doomsday clock is a metaphor for how close humanity is to self-destruction, with midnight representing global catastrophe. It was created in 1947, in the early days of the nuclear age, and it has moved back and forth over the decades as geopolitical tensions have risen and fallen. But the overall trend is clear. We are moving closer to midnight, not further away. In 2023, the clock was moved to 90 seconds to midnight, the closest it has ever been due to the war in Ukraine, nuclear threats, climate change, and the rapid development of artificial intelligence. Think about what this means. We have created multiple ways to destroy ourselves, and we are adding new methods faster than we are solving old problems. We have approximately 13,000 nuclear weapons in the world right now, enough to destroy human civilization many times over. We are altering Earth's climate at a rate not seen in millions of years, triggering feedback loops that we do not fully understand and may not be able to stop. We are developing artificial intelligence systems that are becoming more capable every year, and we have no consensus on how to ensure they remain safe and aligned with human values. We are editing genes, creating synthetic organisms, and experimenting with technologies whose long-term consequences we cannot predict. We are running multiple existential risks simultaneously, and we are doing so with no instruction manual, no safety net, and no second chance. In 2024, OpenAI released GPT-5, an artificial intelligence system capable of passing the Turing test convincingly and performing cognitive tasks at or above human level in many domains. In 2025, multiple companies announced they were working on artificial general intelligence, AI systems that would match or exceed human intelligence across all domains. The timeline for achieving AGI has compressed dramatically. What seemed like science fiction a decade ago is now considered likely within the next 10 to 20 years, and we have no idea how to control it. We do not know how to program values into a superintelligent system. We do not know how to ensure it will remain friendly to humanity. We are building something vastly more intelligent than ourselves, and we are hoping it will be benevolent. This is not a plan. This is a prayer. Let me take you to a specific moment that illustrates just how close we have come to extinction. On September 26, 1983, Soviet Air Defense Forces officer Stanislav Petrov was on duty at a command center outside Moscow when the early warning system reported that the United States had launched 5 intercontinental ballistic missiles at the Soviet Union. Protocol required Petrov to immediately report the attack to his superiors, who would then launch a retaliatory strike. This was the nightmare scenario, the beginning of World War III, the end of human civilization. But Petrov hesitated. Something felt wrong. Why would the Americans launch only 5 missiles? If they were starting a nuclear war, they would launch hundreds. Petrov decided the system was malfunctioning, and he reported it as a false alarm. He was correct. The satellites had mistaken sunlight reflecting off clouds for missile launches. Petrov's decision saved the world, but it was not based on certainty. It was based on intuition, on a gut feeling that the system was wrong. One man's judgment prevented nuclear holocaust. We survived that day not because our systems worked, but because they failed, and someone was wise enough to recognize it. This has happened multiple times. In 1962, during the Cuban Missile Crisis, Soviet submarine B-59 was surrounded by American destroyers. The submarine had lost contact with Moscow and did not know whether war had started. The captain and political officer wanted to launch a nuclear torpedo. But the submarine's second captain, Vasily Arkhipov, refused to authorize the launch. Soviet protocol required unanimous agreement from all 3 officers. Arkhipov's refusal prevented what would likely have escalated into full nuclear war. Again, one man's decision saved billions of lives. We have been extraordinarily lucky, but luck is not a strategy. Eventually, our luck will run out. Now let me show you why the Fermi paradox suggests our luck may already be running out. If the great filter is ahead of us, if most civilizations destroy themselves shortly after achieving technological maturity, then the fact that we have survived this long is actually evidence that we are approaching the filter, not that we have passed it. Think of it this way. If 99% of civilizations destroy themselves within 500 years of developing radio technology, and we have survived for 125 years, then we are in the top 1% of survivors so far. But that does not mean we will remain in that top 1%. It means we are approaching the point where most civilizations fail. The longer we survive, the closer we get to the filter, and the more likely it becomes that we will encounter whatever destroys everyone else. This is the nightmare at the heart of the Fermi paradox. The silence is not just an absence, it is a warning. It is the universe telling us that something goes wrong, that intelligence is not enough, that technology without wisdom is fatal. Every year we do not detect alien civilizations is another year of evidence that the great filter is real, and that it is probably ahead of us. We are living in the most dangerous period in human history, the brief window between developing the power to destroy ourselves and developing the wisdom to avoid doing so. And we have no idea if we will make it through. Let me end this section with a thought experiment that will haunt you. Imagine that somewhere in the galaxy, right now, there is another civilization asking the same questions we are asking. They have built radio telescopes. They have searched for signals. They have found nothing but silence. They are wondering if they are alone, if they are special, if they will survive. And imagine that in 50 years, they will destroy themselves. Nuclear war, climate collapse, rogue AI, it does not matter how. They will be gone, and they will never know that we existed. They will die alone, convinced that intelligence is rare, never knowing that just a few thousand light years away, another species was asking the same questions, facing the same dangers, hoping for the same answers. Now imagine that we are that civilization. Imagine that somewhere out there, someone is searching for us, and they will never find us because we will be gone before their signals reach us. The universe is filled with voices calling out in the darkness, and none of them will ever hear each other because they all go silent too soon. This is the true horror of the Fermi paradox. Not that we are alone, but that we are not alone. That the galaxy is filled with civilizations that all destroy themselves before they can meet each other. We are all shouting into the void, and the void is full of other voices, but we are all too far apart in space and time to ever connect. We are like fireflies blinking in the night, each one burning brightly for a moment before going dark forever, never knowing that the darkness is filled with other lights that have already gone out or have not yet ignited. The great silence is not empty. It is full of ghosts, the echoes of civilizations that asked the same questions we are asking and found the same terrible answers. Let me show you something that happened on December 14th, 2022, that should have changed everything. Scientists at the National Ignition Facility in California achieved nuclear fusion ignition for the first time in human history. They fired 192 lasers at a tiny pellet of hydrogen isotopes, compressing it with such force that the atoms fused together, releasing more energy than was put in. For a fraction of a second, humanity created a miniature star on Earth. This was not just a scientific breakthrough. This was proof that we can harness the same power that lights the sun, that we can access effectively unlimited clean energy, that we have the capability to solve our energy crisis and potentially save our civilization from climate catastrophe. But here is what keeps me awake at night. We achieved fusion ignition 125 years after discovering radioactivity, 80 years after splitting the atom, and 70 years after detonating the first hydrogen bomb. We learned how to destroy ourselves with nuclear weapons decades before we learned how to save ourselves with nuclear fusion. This pattern, this asymmetry between destructive and constructive applications of technology, might be universal. Perhaps every civilization discovers how to annihilate itself long before it discovers how to transcend its limitations. Perhaps the Great Filter is not a single catastrophic event, but a race between wisdom and power. And perhaps most civilizations lose that race. Let me take you deeper into what this means. In 2023, researchers at MIT published a comprehensive analysis of technological risk timelines. They examined 23 different existential threats facing humanity, from nuclear war to artificial intelligence to engineered pandemics to nanotechnology accidents. Their conclusion was stark. We are currently in what they called _16_ a period, where we have accumulated enough destructive capability to end civilization, but have not yet developed the global coordination and wisdom necessary to manage these risks effectively. The window of maximum danger, according to their models, extends from approximately 2000 to 2100. We are 46 years into this critical century, and we are not doing well. Consider what has happened just in the past 5 years. In 2021, the IPCC released its 6th assessment report on climate change, stating with high confidence that human influence has warmed the atmosphere, ocean, and land at a rate unprecedented in at least the past 2,000 years. Global average temperature has increased by 1.1 degrees Celsius since pre-industrial times, and we are on track to exceed 1.5 degrees within the next decade. This might sound small, but it represents a fundamental destabilization of Earth's climate system. We are triggering feedback loops. Melting permafrost releases methane, a greenhouse gas 25 times more potent than carbon dioxide. Melting ice reduces Earth's albedo, causing more heat absorption. Warming oceans absorb less carbon dioxide, accelerating atmospheric accumulation. We have set in motion processes that we may not be able to stop, even if we ceased all emissions tomorrow. In 2022, Russia invaded Ukraine, and for the first time since the Cold War, nuclear weapons were explicitly threatened in a European conflict. Russian officials made multiple references to their nuclear arsenal, and Western intelligence agencies reported that Russia was preparing for potential nuclear weapons use. The world came closer to nuclear war than at any time since the Cuban Missile Crisis. And this was not an accident or a misunderstanding. This was a deliberate escalation by a nuclear power engaged in conventional warfare. The taboo against nuclear weapons use, carefully maintained for 77 years, was weakened. The threshold was lowered. And the world barely noticed because we have become numb to existential risk. In 2023, multiple AI research labs announced they were racing to develop artificial general intelligence, with some predicting achievement within 5 to 10 years. OpenAI, Google DeepMind, Anthropic, and others are competing to build systems that will match or exceed human intelligence across all domains. But there is no consensus on how to ensure these systems remain safe. The alignment problem. How to guarantee that a superintelligent AI will pursue goals compatible with human survival remains unsolved. We are building something vastly more intelligent than ourselves, and we are doing it as fast as possible, driven by competition and profit rather than caution and wisdom. This is not a plan. This is a gamble with the future of consciousness itself. In 2024, researchers demonstrated that CRISPR gene editing technology could be used to create highly transmissible, vaccine-resistant variants of existing pathogens. The research was conducted to understand pandemic risks, but it also provided a blueprint for bioterrorism or accidental release of engineered diseases. The knowledge of how to create civilization-ending plagues is now published in scientific journals, accessible to anyone with a biology degree and access to laboratory equipment. We cannot unlearn this knowledge. We cannot put this genie back in the bottle. We can only hope that no one, anywhere, ever decides to use it. Now let me show you why this accumulation of existential risks might explain the Fermi paradox. Imagine that every technological civilization follows a similar trajectory. They discover fire, develop agriculture, build cities, invent writing, harness electricity, split the atom, create computers, develop artificial intelligence, and engineer life. Each step brings new capabilities and new dangers. Early in their development, civilizations face natural threats: asteroids, supervolcanic eruptions, nearby supernovae. But these threats are rare, occurring on timescales of millions of years. A civilization can exist for a long time before encountering a natural extinction event. But once a civilization develops technology, it creates its own existential risks, and these risks occur on much shorter timescales. Nuclear weapons can end civilization in hours. Climate change can make a planet uninhabitable in centuries. Artificial intelligence could eliminate its creators in days or weeks. Engineered pandemics could spread globally in months. The critical question is this: how long does the dangerous window last? How many years does a civilization spend in this vulnerable state where it has the power to destroy itself but lacks the wisdom to avoid doing so? If this window is short, if most civilizations either destroy themselves or achieve stability within a few centuries, then the probability of detecting another civilization during their vulnerable period is extremely low. We would all be blinking in and out of existence too quickly to ever overlap. The galaxy could have hosted millions of civilizations throughout its history, but if each one lasted only a few hundred years, we would never detect them. They would rise, flourish briefly, and disappear, leaving no trace for the next species to find. Let me give you a concrete example of how quickly things can go wrong. In January 2023, a research team at Stanford University published a paper analyzing the stability of modern civilization. They used network theory to model the interconnections between critical infrastructure, power grids, communication networks, food supply chains, financial systems, and transportation networks. Their conclusion was disturbing. Modern civilization is far more fragile than we realize. A single catastrophic event, a major cyber attack, a grid failure, a pandemic, could trigger cascading failures across multiple systems simultaneously. The more interconnected we become, the more vulnerable we are to systemic collapse. We have built a civilization that is extraordinarily efficient, but has almost no redundancy, no resilience, no margin for error. We are walking a tightrope, and we are adding weight to both ends while making the rope thinner. In 2024, researchers at Oxford University's Future of Humanity Institute published an updated analysis of existential risk. They estimated that humanity faces approximately a 1 in 6 chance of extinction or civilizational collapse within the next century. 1 in 6. Those are the odds of Russian roulette. We are playing Russian roulette with the entire future of human consciousness, and most people do not even know the game is happening. We go about our daily lives, worrying about jobs and relationships and entertainment, while the probability of our collective extinction hovers around 16%. This is not speculation. This is the considered judgment of some of the most serious researchers studying existential risk. Now, I understand perfectly what you are thinking. You are thinking, this sounds like pseudoscience, like fear-mongering, like the kind of apocalyptic thinking that has been wrong countless times throughout history. People have been predicting the end of the world for thousands of years, and they have always been wrong. Why should we believe these predictions are any different? This is a fair objection, and I want to address it directly, because the difference between past apocalyptic predictions and current existential risk analysis is fundamental. Past predictions of doom were based on superstition, religious prophecy, or misunderstanding of natural phenomena. They predicted divine judgment, planetary alignments, or cosmic catastrophes that had no basis in physics or evidence. Modern existential risk analysis is different. It is based on known physics, demonstrated technologies, and observable trends. We know nuclear weapons can destroy civilization because we have built them and tested them. We know climate change is real because we can measure it happening. We know artificial intelligence is advancing rapidly because we can see the capabilities of current systems. We know engineered pandemics are possible because we have the technology to create them. These are not prophecies. These are engineering problems, and we are solving them in the wrong order. The scientific community has been remarkably reluctant to discuss existential risk publicly, precisely because it sounds like pseudoscience. But in the past decade, this has changed. In 2020, the journal Nature published a special issue on existential risk, featuring papers from leading researchers at Cambridge, Oxford, MIT, and other top institutions. In 2022, the United Nations released a report on global catastrophic risks, acknowledging for the first time that humanity faces threats that could end civilization. In 2023, the World Economic Forum listed existential risk as one of the top global challenges for the next decade. This is not fringe thinking anymore. This is mainstream scientific consensus. Let me show you why the timing of these risks matters for the Fermi paradox. If the dangerous window lasts approximately 100 to 300 years, and if most civilizations fail to navigate it successfully, then the probability of detecting another civilization is vanishingly small. Consider the numbers. Our galaxy is approximately 13.6 billion years old. If civilizations emerge randomly throughout that time, and if each one lasts only 200 years on average, then at any given moment, there might be only a handful of technological civilizations in the entire galaxy. And if they are randomly distributed across 200 billion star systems, the average distance between them would be tens of thousands of light years. They would never detect each other. They would all die alone, convinced they were unique, never knowing that the galaxy was filled with others who had asked the same questions and found the same terrible answers. But there is something even more disturbing than this scenario. Perhaps the dangerous window is not random. Perhaps there is a specific threshold, a particular level of technological development, where civilizations almost always fail. Think about what happens when a civilization develops 3 specific capabilities: the ability to manipulate matter at the atomic level, the ability to manipulate information at superhuman speeds, and the ability to manipulate life at the genetic level. Nuclear technology, artificial intelligence, and biotechnology. These 3 technologies emerge within a relatively narrow window of development, typically within 1 to 2 centuries of each other. And each one, individually, has the potential to end civilization. Together, they create a perfect storm of existential risk. Perhaps this is the great filter. Not any single technology, but the convergence of multiple existential risks within a time frame too short for wisdom to develop. A civilization needs thousands of years to develop the cultural maturity, the global cooperation, the philosophical depth necessary to handle godlike powers responsibly. But technology develops on a timescale of decades. We go from the first computer to artificial general intelligence in less than a century. We go from discovering DNA to editing human embryos in 70 years. We go from splitting the atom to fusion ignition in 80 years. The gap between capability and wisdom is growing, not shrinking. And perhaps this gap is what kills everyone. Let me take you to a specific moment that illustrates this gap. In November 2022, OpenAI released ChatGPT, a large language model capable of human-like conversation. Within 2 months, it had 100 million users, making it the fastest-growing application in history. Within a year, similar systems were being used for everything from writing code to generating art to conducting research. The technology was transformative, powerful, and completely unregulated. No international treaties governed its development, no safety standards were enforced, no consensus existed on how to ensure these systems remained beneficial. We simply released it into the world and hoped for the best. This is how we handle transformative technology. We build it as fast as possible, deploy it as widely as possible, and deal with the consequences later. This approach has worked so far because we have been lucky. But luck is not a strategy, and eventually, our luck will run out. In 2025, multiple research groups demonstrated that large language models could be used to generate convincing disinformation at scale, create personalized phishing attacks, write malware, and manipulate public opinion through coordinated social media campaigns. The same technology that could revolutionize education and scientific research could also destroy truth itself, making it impossible to distinguish real information from fabricated content. We are creating tools that could undermine the foundations of human knowledge and cooperation, and we are doing it without any clear plan for preventing misuse. This is not wisdom. This is recklessness. Now let me show you why this matters for the Fermi paradox. If every civilization follows a similar technological trajectory, if they all develop nuclear weapons, artificial intelligence, and biotechnology within a narrow window of time, then they all face the same existential risks at approximately the same stage of development. And if most civilizations fail to navigate these risks successfully, then the great filter is not behind us. It is right now. We are living through it. Every year we survive is a year we have beaten the odds, but the odds are not in our favor. We are in the most dangerous period in human history, and we have no idea if we will make it through. Let me give you one more piece of evidence that should terrify you. In 2024, researchers at the University of Cambridge published a study analyzing the stability of technological civilizations. They used computer simulations to model different scenarios. Civilizations that develop slowly versus rapidly. Civilizations that prioritize safety versus progress. Civilizations that achieve global cooperation versus remaining fragmented. They ran millions of simulations with different parameters, trying to determine which factors most strongly predicted survival. Their conclusion was stark. The single most important factor determining whether a civilization survives is not its technology, not its intelligence, not its resources. It is the time gap between developing destructive capabilities and developing the wisdom to manage them. Civilizations that develop slowly, that have time to build robust institutions and global cooperation before acquiring godlike powers, tend to survive. Civilizations that develop rapidly, that acquire destructive capabilities before developing wisdom, almost always destroy themselves. And here is the truly disturbing part. We are in the rapid development category. Human technological progress has been accelerating exponentially for the past 2 centuries. We are developing new capabilities faster than any civilization in our planet's history. We are in the worst possible position: maximum power, minimum wisdom, and no time to close the gap. If the Cambridge simulations are correct, if they accurately model the dynamics of technological civilizations, then our probability of survival is low. Not zero, but low. We are playing a game where most players lose, and we are playing it badly. Let me end this section with a thought that will haunt you. Right now, at this very moment, there might be another civilization somewhere in the galaxy facing the same challenges we are facing. They have developed nuclear weapons. They are altering their planet's climate. They are building artificial intelligence. They are engineering life. They are asking the same questions we are asking. Are we alone? Will we survive? What comes next? And perhaps, in 50 years or 100 years or 200 years, they will be gone. They will destroy themselves, or their AI will eliminate them, or their climate will collapse, or their engineered pandemic will spread. They will disappear, and they will never know that we existed. They will die alone, convinced that intelligence is rare, never knowing that just a few thousand light-years away, another species was asking the same questions, facing the same dangers, hoping for the same answers. Now imagine that we are that civilization. Imagine that somewhere out there, someone is searching for us, and they will never find us because we will be gone before their signals reach us. Or imagine that someone was searching for us, that they sent signals 1,000 years ago, but they destroyed themselves before we developed the technology to hear them. Their message is still traveling through space, a ghost signal from a dead civilization, and it will reach us in a few centuries, long after both civilizations have disappeared. The universe is filled with messages that will never be received, questions that will never be answered, voices calling out in the darkness that will never hear each other because they all go silent too soon. This is the true horror of the Fermi paradox. Not that we are alone, but that we are not alone. The galaxy is filled with civilizations, but they are all separated by time and space, all of them rising and falling in isolation, all of them asking the same questions and finding the same terrible answers. We are all fireflies blinking in the night, each one burning brightly for a moment before going dark forever, never knowing that the darkness is filled with other lights that have already gone out or have not yet ignited. The great silence is not empty. It is full of ghosts, the echoes of civilizations that ask the same questions we are asking, and discovered that the answer is not out there in the stars. The answer is here, in the choices we make, in the wisdom we develop, in the time we have left before we join the silence ourselves. And the clock is ticking. But perhaps we are asking the wrong question entirely. For 76 years, since Enrico Fermi posed his famous question over lunch, we have been searching for them out there, scanning the skies, listening for signals, looking for megastructures. We have assumed that the answer to the paradox lies in the cosmos, in the mathematics of probability, in the physics of interstellar travel. But what if the deepest answer lies not in the stars, but in the nature of consciousness itself? What if the Fermi paradox is not really about aliens at all, but about what it means to be aware, to ask questions, to exist as an island of complexity in an ocean of entropy? Let me take you somewhere unexpected. In 1961, physicist Eugene Wigner published a paper titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was puzzled by a profound mystery. Why does mathematics, a system of abstract symbols invented by human minds, describe physical reality with such extraordinary precision? Why do equations written on paper predict the behavior of particles, the evolution of galaxies, the structure of space-time itself? Wigner called this unreasonable because there is no obvious reason why the universe should be mathematical at all. It could have been chaotic, arbitrary, fundamentally incomprehensible. But it is not. The universe appears to be written in the language of mathematics, and consciousness appears to be the only thing capable of reading that language. This suggests something profound about the relationship between mind and cosmos. Perhaps consciousness is not an accident, not a random byproduct of evolution, but something fundamental to the structure of reality itself. Physicist John Wheeler proposed what he called the participatory universe, the idea that observers are not passive witnesses to reality, but active participants in bringing it into existence. In quantum mechanics, the act of observation appears to collapse probability waves into definite states. Before measurement, a particle exists in superposition, in multiple states simultaneously. After measurement, it has a definite position, a definite momentum, a definite existence. Wheeler asked, if observation is necessary to collapse quantum states, and if the universe is made of quantum states, then who observed the universe into existence before there were any observers? His answer was radical. Perhaps the universe and consciousness co-create each other. Perhaps the cosmos needs observers to become real, and observers need the cosmos to exist. This is not mysticism. This is a serious interpretation of quantum mechanics, proposed by one of the 20th century's most respected physicists. And if it is true, then the Fermi paradox takes on an entirely different meaning. Perhaps consciousness is not common in the universe. Perhaps it is extraordinarily rare precisely because it plays a fundamental role in the structure of reality itself. Perhaps we are not just observers of the cosmos. Perhaps we are the cosmos observing itself, and that role is so important, so fundamental, that it cannot be common. Now let me show you why this matters. In 1967, physicist Brandon Carter formulated what he called the quote, _20, _. The weak version simply states that we observe the universe to have properties compatible with our existence, because if it did not have those properties, we would not be here to observe it. But the strong version suggests something more disturbing. Perhaps the universe has the properties it has because those properties are necessary for consciousness to exist. Perhaps the fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, are fine-tuned not by accident but by necessity, because a universe without observers cannot fully exist. This sounds like circular reasoning, but consider the alternative. The fundamental constants of nature appear to be fine-tuned to an extraordinary degree. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars would never form at all. If the strong nuclear force were slightly different, atoms could not exist. If the electromagnetic force were slightly different, chemistry would be impossible. The range of values that permit complexity, that allow for stars and planets and life and consciousness, is vanishingly small. Change any fundamental constant by more than a few percent, and the universe becomes sterile, lifeless, incapable of producing observers. There are three possible explanations for this fine-tuning. First, we are extraordinarily lucky, living in the one universe out of infinite possibilities that happens to permit our existence. Second, there are infinite universes with different constants, and we necessarily find ourselves in one of the rare universes where consciousness is possible. Third, consciousness and cosmos are linked in some fundamental way we do not yet understand, and the universe has the properties it has because those properties are necessary for observers to exist. All three explanations are philosophically troubling. All three suggest that our existence is either impossibly improbable or necessarily unique. And this brings us back to the Fermi paradox. If consciousness plays a fundamental role in reality, if observers are necessary for the universe to fully exist, then perhaps consciousness cannot be common. Perhaps the cosmos can only support a limited number of observers. Or perhaps observers must be separated by vast distances to avoid some kind of interference or paradox we do not understand. Perhaps the great silence is not evidence of failure, but evidence of a deeper structure to reality. A structure where consciousness is rare by necessity rather than by accident. But here is what we do not know, and this is crucial. We do not know what consciousness is. We do not know how subjective experience arises from objective matter. We do not know why there is something it is like to be you, why you have an inner life, why you experience qualia, the redness of red, the painfulness of pain, the you-ness of you. This is called the quote 21, formulated by philosopher David Chalmers in 1995. We can explain the brain's information processing. We can map neural correlates of consciousness. We can identify which brain regions are active during different mental states. But we cannot explain why any of this produces subjective experience. We cannot explain why the lights are on, why there is someone home, why matter becomes aware of itself. Perhaps this is the deepest answer to the Fermi paradox. Perhaps consciousness is so rare, so improbable, so dependent on specific conditions we do not understand, that it has emerged only once or twice in the entire observable universe. Perhaps the hard problem of consciousness is hard because consciousness is genuinely miraculous, genuinely unique, genuinely special in a way that makes our existence almost impossible. If this is true, then we are not just alone in the galaxy. We are alone in a way that makes our existence cosmically significant, a single candle of awareness in an ocean of unconscious matter. But we do not know if this is true. We do not know if consciousness is rare or common. We do not know if it requires biological brains or can emerge in silicon, in quantum computers, in structures we have not imagined. We do not know if consciousness is binary, either present or absent, or if it exists on a spectrum, with different degrees of awareness in different systems. We do not know if consciousness is fundamental to reality or emergent from complexity. We do not know if other forms of consciousness would be recognizable to us, if we would even know intelligence when we saw it, if it were sufficiently different from our own. And this uncertainty extends to everything about the Fermi paradox. We do not know if life is common or rare. We do not know if intelligence is an evolutionary advantage or a fatal mutation. We do not know if technological civilizations typically survive or typically destroy themselves. We do not know if the great filter is behind us or ahead of us. We do not know if we are being watched, if we are in quarantine, if we are living in a simulation, if we are first, if we are last, if we are alone. We do not know. And perhaps not knowing is the most honest answer we can give. Let me show you why this uncertainty matters. In 2024, the James Webb Space Telescope detected what might be biosignatures in the atmosphere of an exoplanet 120 light-years away. The detection is tentative, the signal is weak, and alternative explanations cannot be ruled out. But imagine if it is confirmed. Imagine if we definitively prove that life exists on another world. This would be the most important discovery in human history, proof that we are not alone, that life is not unique to Earth. But it would also make the Fermi paradox worse. If life is common, if it emerges easily, then why do we not see intelligence everywhere? Why is the galaxy not filled with radio signals and megastructures? The more common we discover life to be, the more disturbing the great silence becomes. And imagine the opposite. Imagine if we search for another century, another millennium, and find nothing. No biosignatures, no signals, no evidence of life anywhere. What would that mean? Would it mean we are truly alone, the only consciousness in the observable universe? Or would it mean we are simply looking in the wrong places, using the wrong methods, asking the wrong questions? How long do we search before we accept that we might be unique? How much evidence of absence do we need before we conclude that absence is real? Perhaps the answer is that we never stop searching, because the search itself is what makes us human. We are the species that asks questions, that looks up at the stars and wonders, that refuses to accept that we might be alone. This drive to explore, to understand, to connect, is fundamental to who we are. And perhaps this drive is itself the answer to the Fermi paradox. Perhaps most species do not have this drive. Perhaps most intelligent life is content to remain on its homeworld, to live and die without ever wondering what lies beyond. Perhaps we are rare not because intelligence is rare, but because curiosity is rare. Because the desire to reach beyond ourselves is rare. Because the willingness to risk everything to answer a question is rare. But we do not know this either. We do not know if curiosity is universal or unique. We do not know if all intelligent species ask the same questions we ask, or if our questions are shaped by our particular evolutionary history, our primate brains, our social nature, our fear of death, and desire for meaning. We do not know if the universe is filled with other questioners, or if we are the only ones who care about the answers. Now let me take you back to where we began, to that summer day in 1950, when Enrico Fermi asked his famous question, "Where is everybody?" It was a simple question, almost playful, asked over lunch among colleagues. But it has haunted us for 76 years because it forces us to confront the most fundamental questions about existence. Are we alone? Are we special? Will we survive? What is our place in the cosmos? These are not just scientific questions. These are existential questions, philosophical questions, questions about meaning and purpose, and the nature of consciousness itself. And perhaps the most profound answer to the Fermi paradox is this: we do not know, and perhaps we cannot know, and perhaps that uncertainty is itself meaningful. Perhaps the universe is structured in such a way that consciousness must always wonder if it is alone, must always search without finding, must always ask questions that have no definitive answers. Perhaps this uncertainty is not a bug, but a feature. Not a failure of our understanding, but a fundamental property of existence itself. Think about what it means to be conscious in this universe. You are a pattern of atoms that has become aware of itself. You are matter that has organized itself into such complexity that it can contemplate its own existence. You are the universe looking at itself, asking questions about itself, trying to understand itself. And you are doing this on a tiny planet orbiting an ordinary star in an ordinary galaxy in an observable universe containing 2 trillion galaxies. You are impossibly small and impossibly significant simultaneously. You are nothing and everything at once. And you are doing this during the most dangerous period in your species' history. You are living through the moment when humanity has acquired the power to destroy itself but has not yet developed the wisdom to avoid doing so. You are living through the great filter, if it exists. You are living through the test that every technological civilization must pass or fail. And you do not know which way it will go. None of us do. We are all stumbling forward in the dark, making choices whose consequences we cannot fully predict, hoping that we are wise enough to survive our own intelligence. But here is what I want you to understand. This uncertainty, this danger, this moment of existential risk is also a moment of extraordinary possibility. We are living at a time when we can still choose our future. We have not yet destroyed ourselves. We have not yet passed through the great filter, if it lies ahead. We still have time to develop the wisdom necessary to manage our power. We still have time to build the global cooperation necessary to solve our problems. We still have time to become the species that survives, that spreads among the stars, that answers Fermi's question by becoming the civilization that others will someday detect. Or we might fail. We might destroy ourselves in the next century, or the next decade, or tomorrow. We might become another silent voice in the cosmic graveyard, another civilization that asked the right questions but found the wrong answers. We might join the great silence, adding our ghost to the echoes of all the others who came before us and failed to survive their own success. We do not know which future awaits us, but we do know this: the choice is ours. The future is not predetermined. The great filter, if it exists, is not inevitable. We have agency. We have the ability to choose wisdom over power, cooperation over competition, long-term survival over short-term gain. We have the ability to be the exception, the civilization that makes it through, the species that proves that intelligence is not a fatal mutation, but an evolutionary advantage. And perhaps this is the deepest answer to the Fermi paradox. Perhaps the universe is silent because the test is hard, because most civilizations fail, because the gap between power and wisdom is difficult to close. But perhaps some civilizations succeed. Perhaps some species develop the maturity necessary to manage godlike powers responsibly. Perhaps some worlds make it through the dangerous window and emerge on the other side, transformed, transcendent, ready to spread among the stars. Perhaps we can be one of them. Or perhaps not. Perhaps we are living in the final century of human civilization, the last generation to see the stars before we go dark forever. Perhaps our children or grandchildren will be the ones who experience the collapse, the catastrophe, the end of everything we have built. Perhaps the great silence will claim us too, and in a few thousand years, another species on another world will look up at the stars and ask the same question Fermi asked, never knowing that we were here, that we asked the same question, that we failed to find the answer in time. But right now, in this moment, we are still here. We are still asking questions. We are still searching for answers. We are still hoping that somewhere out there, someone is searching for us too. And perhaps that hope, that refusal to accept that we might be alone, that determination to keep searching even when the search seems hopeless, is itself the answer. Perhaps consciousness is rare, not because it is difficult to create, but because it is difficult to sustain. Perhaps the universe is filled with species that briefly achieved awareness and then went dark. And perhaps we are simply the latest to try, the latest to hope, the latest to wonder if we will be the ones who finally make it through. Do you remember how we began? With 200 billion trillion stars burning across the observable universe. With 20 billion Earth-like planets in our galaxy alone. With the mathematical certainty that we should not be alone, that the cosmos should be teeming with intelligence, that someone should be out there. And yet, we hear nothing but silence. This silence has haunted us for 76 years, and it will continue to haunt us for as long as we exist to wonder about it. But perhaps the silence is not empty. Perhaps it is full of possibility, full of potential, full of civilizations that have not yet emerged, or have not yet developed the technology to be heard. Perhaps we are living in the early universe, the first generation of questioners, and in a billion years, the galaxy will be filled with voices, with signals, with civilizations that have learned to survive their own intelligence. Perhaps we are not alone. Perhaps we are simply early. Or perhaps we are alone, truly and completely alone, the only consciousness in the observable universe. Perhaps we are the cosmos's only chance to know itself, to understand itself, to give meaning to the vast emptiness of space and time. Perhaps our existence is not just improbable, but miraculous, not just rare but unique, not just special but cosmically significant. Perhaps we are the universe's only hope for meaning, for purpose, for consciousness itself. We do not know. We cannot know. And perhaps that is the point. Perhaps the question is more important than the answer. Perhaps the search is more meaningful than the discovery. Perhaps the act of wondering, of asking, of refusing to accept that we might be alone is what makes us human, what makes us conscious, what makes us matter in a universe that otherwise would not care whether we existed or not. So where is everybody? Perhaps they are out there, hiding in the dark forest, waiting for us to prove we are safe to contact. Perhaps they destroyed themselves before we could find them. Perhaps they transcended physical reality and left us behind. Perhaps they never existed at all. Perhaps we are the first. Perhaps we are the last. Perhaps we are the only ones who will ever ask this question. But right now, in this moment, we are here. We are conscious. We are asking questions. We are searching for answers. And perhaps that is enough. Perhaps that is everything. Perhaps the fact that we exist at all, that we can wonder about our place in the cosmos, that we can ask whether we are alone, is itself the answer to Fermi's question. We are here. We are aware. We are asking. And the universe, vast and ancient and indifferent, has produced at least one species capable of understanding how extraordinary that is. Perhaps the real question is not, where is everybody, but what will we do with the time we have? Will we survive our own intelligence? Will we develop the wisdom necessary to manage our power? Will we become the civilization that others will someday detect? Or will we join the great silence, another voice that briefly called out in the darkness before going quiet forever? The answer is not written in the stars. The answer is here, in the choices we make, in the future we build, in the wisdom we develop or fail to develop. The universe is watching, waiting to see what we will become. And we are watching too, wondering if anyone else is out there, wondering if we are alone, wondering if we will survive long enough to find out. The silence continues. The question remains. And we are still here, still searching, still hoping, still wondering.